Imagine you're the CTO at a global enterprise, buried in petabytes of supply chain telemetry, market volatility signals, and customer behavior data that classical systems keep approximating because the true optimal solutions hide in an exponential sea of possibilities. Your teams run the numbers for days, burning compute hours and still leaving millions in potential savings or missed opportunities on the table. Then, one morning, you log into a familiar cloud console, select a quantum backend, upload your model, and watch a quantum processor evaluate countless combinations simultaneously delivering near-optimal routes, risk profiles, or molecular designs in minutes instead of weeks. No cryogenic lab, no million-dollar hardware purchase, no army of physicists on payroll, just quantum power rented by the shot or the hour. That's Quantum as a Service, QaaS, and it's already delivering measurable edges to forward-thinking companies right now in 2026. What makes QaaS such a breakthrough for enterprise data processing is how it turns quantum computing from an exotic lab curiosity into an on-demand accelerator you can weave into existing cloud workflows. You don't buy the hardware. You access it through platforms that handle the heavy-lifting cryogenic cooling, qubit calibration, error mitigation, all behind a simple API or notebook interface. This pay-as-you-go model means your data scientists can prototype, test, and scale quantum-enhanced jobs without CapEx that would bankrupt most IT budgets. And because it's cloud-native, it scales with your needs. Start with classical simulators for development, graduate to real quantum processing units for production pilots, and integrate results straight back into your classical pipelines. To appreciate the value, let's talk about the quantum difference without the physics textbook overload. Classical bits are strictly 0 or 1. They process sequentially or in massive parallel clusters, but still hit walls on problems where variables explode combinatorially. Qubits, by contrast, leverage superposition. They can be 0, 1, or any probability blend of both at once. Stack a few entangled qubits together and their states link so tightly that measuring one reveals information about all of them instantly. It's like having parallel universes exploring solution spaces simultaneously, rather than one brute force search at a time. For enterprise workloads, this translates to exponential speedups on specific hard problems. Optimization, where you must test every feasible combination. Simulations that model quantum scale interactions directly. Or machine learning kernels that sift high-dimensional data for hidden patterns classical methods overlook. Current hardware sits in the noisy, intermediate-scale quantum era, meaning dozens to a few hundred qubits with some error rates from decoherence, the tendency of fragile quantum states to collapse from tiny vibrations or stray electromagnetic fields. That's why hybrid quantum classical architectures dominate QaaS today. Your classical servers handle data ingestion, feature engineering, and outer-loop optimization loops, while the quantum chip tackles the core subroutine that benefits from superposition or entanglement. Error mitigation techniques, like zero-noise extrapolation or dynamical decoupling, further squeeze usable results out of today's imperfect machines, turning noisy intermediate-scale quantum into practical value rather than waiting for tomorrow's fault-tolerant systems. The leading QaaS platforms have matured into full ecosystems that enterprises can adopt today. One offers superconducting qubit processors, with roadmaps pushing modular multi-chip designs for thousands of logical qubits down the line, complete with open-source toolkits that let developers write circuits in Python and run hybrid jobs seamlessly. Another aggregates hardware from multiple vendors superconducting, trapped ion, neutral atom, so your team can benchmark which qubit modality best fits a particular workload without vendor lock-in. A third emphasizes deep integration with classical cloud services, enabling smooth handoffs between GPUs for training and quantum resources for variational optimization. Specialized providers deliver high-fidelity trapped ion systems or annealing machines tailored for pure optimization tasks, all accessible through unified consoles or APIs that feel as straightforward as spinning up a virtual machine. The real power shows up in concrete enterprise use cases that directly attack data processing bottlenecks. Take logistics and supply chain optimization. The vehicle routing problem with thousands of shipments, dynamic traffic, fuel costs, and delivery windows is NP hard. Classical heuristics give decent approximations, but leave room for massive inefficiency. Quantum approximate optimization algorithms run on QaaS hardware explore the solution landscape in superposition, surfacing route plans that can cut fuel use, delivery times, and emissions by double-digit percentages in pilot-scale tests. Companies have modeled real-world cargo loading on aircraft or container ships, factoring weight distribution, stability, and custom schedules. Problems where even small improvements cascade into millions in annual savings across global fleets. Finance teams are seeing even more immediate ROI. Portfolio optimization under hundreds of correlated assets, regulatory constraints, and stochastic market scenarios overwhelms classical Monte Carlo methods. Quantum algorithms accelerate sampling from complex probability distributions, delivering more accurate risk profiles and trade recommendations faster. One major bank ran a hybrid model on real historical bond trade data and achieved roughly 34% better prediction accuracy on whether orders would fill at quoted prices, directly informing higher confidence trading strategies and reduce slippage. Derivative pricing, credit risk modeling, and fraud detection all benefit similarly because quantum kernels can capture non-linear correlations that classical feature maps miss. In life sciences and materials, QaaS shines for molecular simulation. Classical computers approximate quantum behavior with methods that lose fidelity as molecule size grows. A quantum processor simulates electron orbitals natively because it operates under the same physical rules. Pharmaceutical teams use variational quantum eigensolvers through cloud access to screen candidate drug molecules for binding affinity far quicker than wet lab iteration, compressing discovery timelines that traditionally cost billions in years. Battery chemists model new electrode materials for higher energy density, while energy firms simulate catalyst reactions to improve hydrogen production efficiency, all without owning the hardware. Quantum machine learning adds another layer. Variational classifiers, or quantum support vector machines, process high-dimensional enterprise datasets, customer segmentation, sensor streams, or genomic profiles with potential advantages in feature space exploration. Early results suggest better generalization from smaller training sets, which matters when labeled data is expensive or scarce. These aren't theoretical. They're running today on hybrid QaaS stacks, where classical neural nets feed parameters to quantum circuits and receive back optimized embeddings. None of this is risk-free. Noise remains the biggest practical hurdle. Circuits deeper than a certain length accumulate errors that swamp the signal. Qubit counts limit problem size, talent is scarce, and latency between classical orchestrators and quantum backends can bottleneck tight loops. Security teams must plan for post-quantum cryptography because sufficiently powerful quantum machines could factor large numbers or solve discrete logs that underpin current encryption. Yet QaaS platforms mitigate these realities with built-in simulators for safe testing, automated error mitigation libraries, and managed hybrid orchestration layers. Enterprises start small. Identify a narrow pain point suited to quantum combinatorial optimization or quantum native simulation. Prototype on classical emulators, validate against classical baselines, then scale to real hardware for proof-of-value runs measured in dollars saved or insights gained. Adoption is accelerating because the economics work. You avoid the multi-million-dollar capex and ongoing maintenance of on-prem quantum rigs while gaining immediate access to the latest processor generations as providers upgrade. Roadmaps point toward logical qubits with active error correction within the decade, modular scaling, and even specialized quantum accelerators that slot into data centers like GPUs do now. When that happens, QaaS will evolve from experimental edge to core infrastructure, much the way cloud computing itself went from novelty to necessity. For data leaders watching this, the takeaway is urgency wrapped in practicality. Begin by auditing your workloads for quantum advantage signatures, problems with exponential search spaces, or quantum scale physics. Experiment with free tiers or low-cost simulator access to build internal muscle memory. Partner with platform providers who offer consulting and co-development paths, so your team isn't reinventing quantum programming from scratch. Measure everything: runtime, solution quality, total cost of ownership. The organizations doing this quietly today are the ones who will own competitive moats tomorrow when quantum advantage broadens. QaaS isn't replacing classical computing. It's augmenting it into a hybrid powerhouse that processes enterprise data at scales and accuracies we only dreamed of a few years ago. Supply chains become resilient. Financial models become prescient. Discovery pipelines become lightning fast. The first movers aren't waiting for perfect machines. They're renting the imperfect ones that already deliver value and learning how to extract every qubit of advantage. If your enterprise lives or dies by data processing speed and insight depth, the quantum cloud is already open for business. The question isn't whether this future arrives. It's whether your organization will be ready to harness it when it does.